sensing point of view, because and also one thing to note is that the black dots are in the places where the measurement or the amplitudes are the highest. The red dots where there's a mismatch, and in this case there's 3 places that there's mismatch, are in the places where the amplitudes are also fairly small. So that doesn't give you that much distortion. So we said, okay, can we put this into some sort of framework for our recovery without changing anything on the transmitter side at all? Because the transmitter side is where your power constraints are the highest, so you want to keep that as low as possible, as small as possible. So we said, okay, we started with the basis pursuit recovery, and we added only one small modification, which is this term over here, from the Z tilde to the Z tilde over subset T, which is the support, what is called the support of the signal in the wavelet domain, which is essentially the indices or the positions at which we know the signal will occur. So there is some sort of, you're doing some sort of prior knowledge. But the problem is that we don't have this prior knowledge because we don't have the support a priori. So we said, okay, so maybe this will work, but we don't know where this T comes from in the first place. So we tried 2 or 3 different things. One was, let's just use the difference between 2 adjacent spikes. And that didn't work well at all. And the reason that didn't work well at all is that if you look at a distribution of how much the difference is between spikes, it's really wide and it's all around the place. And actually the mean is close to, in this case, is about 80% because this tail I cut off, which is also pretty big. So there's an 80% difference between spikes in terms of their magnitude. So we said, no, that's not going to work at all. That's not encoding the similarity that we want to. The other thing that we tried is to look at 2 different spikes only in their indices and said how much energy is there in just the mismatch. And that's what this turns out to be. And that's pretty good. It's about a 28% difference overall across the 500,000 or 600,000 spikes that we were looking at. And then it occurred to us that, actually this doesn't work really well because there's a lot of 2 consecutive spikes will be very different because they'll come from different neurons. And so we said, okay, let's try to learn the support over time by increasing the rate at first and then reducing the rate as we have more learning. And so what we found was that if we did that and just added the support that we learned over time to the set, we had a really sharp spike of this at a very low error norm. And this is about 3% or 4% in terms of differences in similarity. So what this means is that basically the mismatch, you need to only account for extra measurements in terms of that 3 or 4%. And so what we did was we added a recovery, an additional block here, which fed back to the CS recovery. We don't change anything here. And this is what the result looks like. And we have a much higher SNDR for the same number of measurements. We didn't change anything at all at the transmitter side. It's only a receiver side algorithmic difference. And that gives us a boost to about a 43x compression. And we said, okay, we can even compare it with an Oracle system if we know the data beforehand, we know the support beforehand. And so we are not that far off from the Oracle as well. And it's interesting that when you go on adding the support, the size of that support set, actually the size of that T, only goes up to about 20. And remember, the actual sparsity is about 11 or 12. It only goes up to about 20, 21, and then stays there across 1,000 spikes. So within the first 30 spikes, you've learned everything you needed to know about all the spikes that are going to come within about 1,000 spikes. I'm just going to skip this for lack of time. So this is the sorting performance, which is what the neuroscientists care about also. And the green one is the Oracle one, and the red one is our proposed technique, which is called the learned union of supports. And the black one is the conventional method, and we're sort of at about 14 or 15 measurements to get a 90% accuracy across, instead of 48 or 64 measurements per spike. And this is what the spikes actually look like before they were compressed, and this is their sorting performance, and this is what the distortion looks like because we reduced the compression down to about a third. And you still get about 90% accuracy, and which is pretty good for the neuroscientists. In terms of power, we can talk about how much power this took, and this is a comparison and this is what the amount of power it would take for the raw signal to be sent out, and the x-axis is the spike rate. Since we are encoding, detecting, and aligning spikes, it's the spike rate matters, and the 24 CS measurements is if you want about a 20 dB SNR, and the 12 is if you want a 90% sorting accuracy. So you won't get a good SNR with just 12 measurements, but you'll get good sorting accuracy, and which is what's all that some people need. And that's pretty much it. We've demonstrated that you get a 2x compression for compressing the spikes for a fairly decent SNR. And if you want to do only sorting, you can do it at even lower rates. And you don't need to do very much on the transmitter side. We have an 8-channel FPGA implementation right now, and since we have a circuits group, they're building the ASIC for a 16-channel version as well. And so, and all the code and the data is at my webpage.
Okay, this talk is open to question and answer. Please.
My understanding of compressive sensing is that the main advantage is that you take fewer samples. I mean, just one of the reasons why it's called compressive sensing. It seems that you're taking the standard number of samples and using compressive sensing almost entirely as a compression method after, for example,
right, post facto. Okay, so that's a great question. So there's in my head, I classify compressed sensing as two parts, which is the hardware compressed sensing, which is what you're talking about, which people have talked about for the last 5 years, and unfortunately doesn't exist. People have come up with techniques to do some things in hardware where you actually do the compressed sensing before you sample. All right, and the reason that's really hard is because it places constraints on the analog design that are so strict that you lose the power advantage that you wanted to have in the rest of the system. And so people have been trying to figure out that whole aspect, and I am actually currently working on an analog domain system for that. But it's, let me just say that it's hard when you're trying to balance it from a holistic point of view. And so this work is, the reason that we could use this similarity is because we already had an ASIC implementation of the spike detection and the alignment, which is already a hard problem. So Webhub, who's the second author on this paper, has already built 2 chips that do this, and he has a 3rd chip that does the spike sorting also on chip. But the power that he requires to do that is so much higher that we are looking for a different approach here.
This is Wenyao from UCLA. I have a question that how do you find the neural signal is compressible in wavelet domain?
Oh, that is also a great question. That is actually magic, and a lot of people have been looking at neural signals and also been trying to do the compression on chip. So we are talking about compressed sensing on chip. but people have tried to do different sorts of compression on chip, but that turns out also to be very expensive in terms of power. And they've already demonstrated that a DWT wavelet with a Dobshish mother wavelet is pretty good. I have a lot of other work which is about using different bases. There are, or the transform domain, there's a lot of other work in compressive sensing that looks for the basis itself. One great example is PCA. You could just use PCA if you're going to learn the basis on the fly. So we are learning the support or the indices on the fly. You could also learn the basis on the fly by adding a few more measurements up front to learn the basis, and then as you go along, as you get better at learning the basis, you can reduce the number of measurements.
Further question? Please.
I was wondering if you have looked at the relationship between M, N, and K, which N is the input, the size of the input signal, M is the signal in the compressed domain, and K is the sparsity. And you know that that's very important when you wanted to do basically compressive sensing. You have to look at the relationship between these three. That to come up with a path matrix. That's one question. And the other question is that what kind of random matrices you look that you use? Did you use Gaussian random generation or database friendly distribution or there are three?
Yes, I understand your question. So in terms of the first question there, I think the 2005 Candies paper, Candies, Sternstow, and Justin Romberg, that paper laid out the foundation for exactly that, that relationship between M, N, and K. I didn't put it there because it's sort of complex to explain unless you have 20 minutes to explain that equation. But yes, that relationship exists, but for that you need to know upfront what is the number of coefficients. And in this case, we did all this analysis up front, so we know like 12 is the magic number for each spike. But if you didn't know that, then you have to estimate that also on the fly, which is another problem altogether. So as far as the second question is concerned, the matrix that I showed is a Bernoulli random IID plus minus 1. So you toss a coin. If it's heads, you do a +1, tails -1. And a lot of people in compressive sensing also use the Gaussian random matrix, as you're saying, which is essentially an IID random variable that you pick from a Gaussian distribution. And that's expensive from an implementation point of view because generating a Gaussian random number, a good Gaussian random number, is expensive. Whereas this one is a uniform random number. I can do it with an LFSR, and that's what we've done in the implementation. Excuse me? Yes, okay, so that segues into another question, which is, does it need to be random or can it be deterministic?
Because when you want to recreate, reconstruct your signal, you have to do the same metrics, otherwise you cannot.
Correct. And so what we do is that whenever we generate it, we just keep the seed of the random number generator, and we regenerate it on the other side based on that seed. And the reason we do this, and some people have shown that you can use deterministic just as well. The only reason that people are conservative about the random matrix generation is because at some points your matrix has to be incoherent with every DWT combination, and it's shown that through random matrix algebra that that holds with an exponentially high probability. Now, the second thing is that for ASIC development, the most expensive thing actually is RAM. And so by generating this on the fly using an LFSR, and this is like a 13-bit LFSR, it's easier to generate it in hardware in circuits than actually to keep that whole matrix in RAM and read those values out each time. So does that answer? Yeah.
Okay, the time over. We thank you.
Thank you very much.
Okay.